All right, for those of you waiting, thanks so much for waiting. I'm just admitting a couple of folks as they come in, and we'll get started shortly. All right, folks, I want to take a moment and welcome all of you here. It looks like we've got pretty much everybody's been let in. I'm keeping an eye on the waiting room too, in case some folks need to be bounced in here. But hey, welcome to Galvanize's Data Science Demo Day for San Francisco. Really happy to have you join us today. This is the culmination of these students' past couple of weeks of work, and the past 12 weeks, they've been working toward becoming data scientists. And I'm really excited for them to share their work with you tonight. And so I want to thank you for taking the time out of your day to come take a look at it. For those of you who don't know me, my name is Jenny Engard. I am the program lead for Galvanize Data Science in San Francisco. And so I have the distinct pleasure of helping shepherd these folks across the finish line. And man, what a crew we've got for you tonight. We've got 12 presenters this evening with topics that are ranging from air pollution to computer vision in terms of like lane detection. We have some stuff about sex trafficking. We have a lot of different projects that are waiting for you to discover. And I hope you get a chance to discover every single one of them tonight. I'm going to go over a couple of talking points and a couple of details, a little bit of meeting hygiene, and then I'm going to open up these breakout rooms so that you can get to the project. So first of all, let's talk about who we are and what we do. We offer a 13-week data science immersive program where our curriculum breaks down the fundamentals and building blocks within the data science industry. And our folks learn and develop their technical skills in engineering and statistics, machine learning, and language processing, and advanced applications, as well as additional professional skills that they'll end up using in the industry. And for the past week and change, our data science students have been working on a self-directed data science capstone, and that demonstrates their creativity, their ingenuity, and their technical expertise. I'm really excited to have you all here today to check it out. Let's kind of talk about some Zoom logistics and meeting hygiene. As the slide says, by now, this is not your first rodeo with COVID and with Zoom. So what I'm going to say right now is just these are going to set some norms so that we have a good time. Couple of things to keep in mind. Make sure you're muting yourself in Zoom. so that you're not distracting the presenter. Obviously, come off of mute to say hi. If you're asking questions, that's totally okay. Another thing that I want you to do is keep your camera on. It's so tempting to hide behind a shutdown camera. We want to see who we're talking to. It helps us read the room, and it's just way more engaging. We don't bite, I promise. And even if we did, we couldn't reach you through the screen, so don't worry. Also, just try to avoid any noisy or distracting backgrounds, and just to be helpful for our students as they're building contacts, provide your first and last name in your screen name for the video chat. It helps us with our conversations and questions and whatnot. All right. So for this evening's presentations, I'm going to talk to you about how this is going to work out. We're creating 3 breakout spaces, actually 4 rooms, including our admissions folks. In these groups, each group is going to have 4 presenters as well as a staff member to moderate and keep your conversation going. Our students are going to be allotted about 5 minutes for the presentation, and then audience members will be given about 5 minutes for questions afterwards. At any point, you can join any breakout room that you want to once they are open. All you need to do is click on the icon with the 4 squares at the bottom of your screen in the option bar that shows share screen. And the breakout room option should be on the bottom right-hand side as it's noted in these images. If you have any issues joining a breakout room, double check that you have the most recent version of Zoom installed on your machine. And if you're still stuck, all you need to do is exit out to this main room right here. We have one of our fantastic DSRs, Juliet. Juliet is going to be on hand to help you out and get you to where you need to be. So if all else fails and you need to get somewhere and you can't get somewhere, talk to Juliet. Juliet's going to help you out. All you have to do is exit the whatever breakout room you're in and head back into this main room. Really, we just want you to see everything that's happening tonight. And I hope you see every single project tonight because they are all really, really good. That being said, I'm going to show you who is going to be in which room here. And so we have 4 different rooms. So we have our first group, which we have 3 groups of 4 students each. I'm also going to share with you the link to the virtual program, which you probably already do have. Give me a second to open up my chat window. I have way too many windows open right now. Give me a second here. And let's get that out to you. I will share that link to you. Make sure that you navigate through that. Make sure you navigate through this. Hang on, sorry. There we go. Make sure you use this document. You can navigate through it. It's pretty interactive, and it will give you a little bit of a synopsis of everything that is happening in each of these breakout rooms. The program is divided up in order of the breakout rooms. So group room is going to be first, group 2 is second, and group 3 is obviously third. And then for those of you that are just joining us or just visiting us and haven't had a lot of time to get to know Galvanize as a company or as an institution, our wonderful enrollment advisor, Itzel, is actually going to be on hand, and she is going to be in the admissions breakout room. Feel free to hop into that room if you have questions about our program or if you want to learn more about what the application process is like and how to get started with us, because we would love to have you as a part of our journey. That being said, I'm so pumped to have all of you here. I'm going to go ahead and open up these breakout rooms. Again, you can visit them in any order that you want. You can stay as long as you want and have a good time. All right, folks, we'll see you shortly.
So many choices.
So many. Hey, good to see you.
Good. You too.
All right, Julia, I'm going to give you host privileges.
Oh, it's great to see a busy room. It's always nice to see that these topics are of interest to so many people. So to get started, I'm Michelle. I'm one of the data science instructors here at Galvanize in San Francisco. And tonight we've got some talks from humor detection to detecting fake reviews, detecting sex trafficking, and on the latter side, music for the tech people who want to get into the nitty-gritty of it. We've got some sequential LSTM models. We've got some CNNs and good old regression. So I'm hoping that there's something for everyone here. And before I go on to introduce the speakers tonight, I want to say, feel free to ask questions at any time. Best is just unmute yourself and ask a question after the presentation. I promise we don't bite. And we can have a nice informal conversation after the presentations. If you don't feel comfortable coming off mute, put it in the Slack, in the channel here in the Zoom group, and I'll make sure we get to your question. All right, so we have 4 speakers in this room. And first up is Kelly Zhao. She's a data scientist with background in statistics from Cornell University, and then went on to do program management and consulting. And we were very glad to have her here with us for these last 3 months. It's been a fun time, not only because her project focuses on humor and humor detection and reviews, but also because she's a genuinely nice colleague to have around. Kelly, I'm going to hand over to you. You can start.
So thank you so much, Michelle. Hi, everyone. My name is Kelly, and I'm excited to talk to you guys about my project today. So let me go ahead and share my screen. Can you guys all see it? Awesome. All right, so my project was about detecting humor in Yelp reviews with LSTMs. So the question I had going into this project was, how can you best detect humor in text data when humor is known to be a higher order language structure versus just regular words and phrases that can be detected using word counts? So to answer this question, I use natural language processing and deep learning to predict humor in reviews using the Yelp Open Dataset, which contains about 8.6 million reviews. And the use case for this sort of study can be applied in building AI systems such as chatbots and virtual assistants, as humor detection can enhance the overall user experience by identifying and injecting humor in conversations. So to start, I took a look at the distribution of the funny votes in each of the reviews and found that it was heavily right skewed. And in a data set like this, it would be hard to do a regression sort of problem. So I opted to turn this into a binary classification problem of funny versus not funny. And after inspecting the reviews themselves, decided to define funny as having 3 votes or more to account for noise in the 1 and 2 votes. In total, that gave me about 340,000 reviews, which came out to be about 4% of the minority class, or the funny class. So before I could feed my data into the models I chose to use, I had to do some text processing to get them into the correct format. For a baseline model, I chose a logistic regression, which involved cleaning the text, tokenizing the text, and then transforming them into a TF-IDF matrix, which accounts for word counts in each of the reviews. As for the LSTMs, I followed a similar text cleaning process and tokenization process, but after that, I created sequences of the words and then used sequence padding to get all the sequences into the same length of 200 words. So as for my modeling, I chose 4 different types of models to compare. The first was the baseline logistic regression. And for the LCMs, I chose 3 architectures. The first one was 1 layer of 100 memory units. Second had 2 layers of 100 memory units. And the third one was a bidirectional layer of 50 units looking both forward and backwards. The results of my modeling showed that precision was pretty even across the board, across all models. The recall did go up significantly between the logistic regression and the bidirectional LSTM. And although 10% precision might seem low, it is actually about 2.5 times what you would get by randomly guessing a funny review in the distribution of the data, about 4%. So it's actually not too bad. And I also chose to optimize for recall in this problem because doing so would allow us to minimize false negatives so that when you find a funny review, it is in fact funny versus potentially being a non-funny review. Seen another way, the results showed that although the bidirectional LSTM had the highest recall, the LSTM with one layer, or the simplest architecture, actually seemed to reduce false negatives the most at 24%. And so some final thoughts from this project were that humor is heavily context dependent. By fitting a bidirectional LSTM, I was able to confirm that signals of humor can be given by surrounding words in both directions, not just forward. However, more layers slightly improved performance, and the bidirectional LSTM did improve performance as well in terms of recall, but not necessarily in reducing false negatives. And so sometimes a simple classification model, such as logistic regression, may suffice, especially when it takes a lot longer to run than training neural networks for hours. So next steps for this project, I would like to use transfer learning with the famous BERT model that Google came out with in 2018, which was trained on a large corpus of Wikipedia and book corpus data. The model contains about 110 million parameters, so it's very robust. It would likely boost my scores. And I would also like to create a humor text generator based on the winning model from that. And now I'll open it up to any questions.
I have a question.
Shoot.
So I'm very curious, with your data set being like 4% of the target label, how did you handle the huge misbalance there?
So there were multiple ways I could have done this. I could have chose to assign class weights, to do oversampling, or to just keep the class weights the same and not balance the data set. Ultimately, I decided to use undersampling so that I had a balanced training data set of about 270,000 funny and not funny reviews. But in order to stay true to the original distribution of the data, I still tested it on the I still created a separate test set that had about 4% of the funny reviews, hence the low seeming precision. If the test set had also been balanced, then likely precision would have been higher.
Okay, gotcha. All right, thank you.
I've got a question, Kelly. Did you try any clustering of the text and to try to make a prediction from that?
I actually did not. I did not get around to that, but that was definitely something I considered doing. I could have done some topic modeling in order to see if I could come up with different categories of humor and see if that would maybe translate into interesting features I could feed into my model. Unfortunately, I'm out of time. But that would probably be good next steps to explore the data further.
Thanks. Any other questions for Kelly? Going once? Going twice? All right. Then up next is Ken Shrivastava. Ken comes with a background in materials and industrials design, but also a passion for music, which is what his capstone is about tonight. Ken, take it away.
Perfect. Thank you, Michelle. Let me get my screen share going here, and we'll jump right into it. All right. Hello, everybody. So again, my name is Ken Shrivastava. Thank you all so much for being here. Today, I'm going to be discussing my project on music genre classification, and more specifically, predicting song genre using raw audio via deep learning models. So getting right into it, a little bit about the workflow and the progression throughout this project. I started by having to restructure directories as a means to store the audio files that I was going to then process through my deep learning models. Once I had all of these audio files stored securely, then I was able to convert all of the audio into MEL spectrograms. MEL spectrograms are a visual representation of the audio, which is a necessary step in order for me to process them through my deep learning models. It was later found that for my purposes, which I'll explain a little bit more, I wanted to convert the data into single dimensional data so that I could better process it through my models. And so I did that, performed some EDA. Finally, when I went to full-blown modeling, I transitioned my data to AWS so I could use their cloud computing to better, again, process my data. do some modeling, and finally deploy the best model that I got on a web app for personal use, which again, I'll show a little bit later. So a little bit about the data set that I'm working with here. In the field of music information retrieval, the Free Music Archive data set's really popular. For my intents and purposes, I use their smaller data set. So this is comprised of 8,000 songs. Each song has just a 30-second clip, and they're equally balanced to 1,000 songs across these 8 genres. Going into my EDA, a little bit about the data itself, the metadata associated with each of these tracks. So genre, the date that the song was created, the composer, the artist. The data set was a little bit sparse, so there wasn't a lot of insights to draw from the data that was there, but this was the most valuable graph that I generated. So as you can see here, we have tracks per year per genre. And so what this tells us, it's a little bit dense, but the key takeaway that I want you to get from this is that we can see that the music that was pooled for this data set spans from 2008 to 2016. And across this roughly 10-year period, we can see that the number of songs per genre is roughly level, barring this outlier with instrumental having a lot of the songs in its 1,000 come from 2015. So what that means is that if we have an evenly distributed distribution across this wide year span, hopefully the data is a little bit more robust, which will in turn make our model more robust and less susceptible to seasonal or like yearly trends in certain genres, and allow us to better predict genres over time as they change. Coming to my model, this is my final model architecture. There was a lot of different iterations that led me to this final path, but for the sake of brevity, I have a CNN. I'm using 3 CNN layers, 3 convolutional one-dimensional layers, followed by an LSTM layer. And so as mentioned at the top, the idea with this architecture for my deep learning model is that each of these convolutional neural network layers is interpreting smaller features in the audio, which again is one-dimensional at this point. And you're feeding these smaller but increasingly large features over to the next layer, over to the next layer, until finally you get to this LSTM, which can take that process data and hopefully discern longer-term temporal trends in the audio. So basically, in layman's terms, maybe this will allow it to make out the rhythm, the beat, the cadence of the song, and hopefully then be able to discern the genre for that song better. Coming to model performance, again, for the final optimized model, I had a baseline of 12.5%, which makes sense. If it's 8 genres and it's choosing essentially at random, that's about 12.5%. So that's our starting point. From the final model, after doing some hyperparameter tuning and working with it, the best accuracy that I was able to achieve was 49.3% with this CNN LSTM configuration. Worth noting, I chose to use exclusively accuracy as my metric for measuring performance for this model because we're kind of indiscriminate about which genres. We want all genres to predict equally well. There isn't a reward or penalty for picking any one genre more accurately than the rest. So this was my intent with going forward with just mainly accuracy. And so I'm currently working on a web app to deploy that final model that I built. And so you'll be able to upload your song, any audio, and it should be able to use that audio and make a prediction itself and output a radar chart similar to this, where of the 8 genres that I used to train the model on, it could tell you which genre that your audio falls most likely into. And so in this example case, it's likely a folk song with maybe some influence from rock or something to that effect. And I think with that, that brings me to questions. Thank you.
Hey there, Ken. This is Joseph Wilson.
Hey, buddy.
So, I'm curious, on the web app side, and also you touched on Amazon, AWS.
Yes.
How far did you get into deploying it in the cloud at this point?
Okay, so yeah, to backtrack a little bit, when I was working with the data, again, for computing, I transitioned all of my data over to AWS, and I was able to get the EC2 running in order to train and like perfect my models. As for deploying the web app itself, I've currently got it working locally. I don't think I'm going to be using AWS long-term because I would like to keep the project alive, so I'm likely going to deploy it on Heroku. I've got all of the functions lined up in a Py file, and I have everything running, but I haven't deployed it to the web yet.
Gotcha. Okay. Nice job.
Thank you.
Hey, Ken, how you doing?
Hey, Alex, how's it going?
It's going great. Face to the name.
Yes, absolutely.
First off, great presentation. Sorry I missed the first bit of it. I was in another room. Excellent job, honestly. And I appreciate that you took some feedback from our previous conversations. Loving the radar chart, man. Looks great. Tells a good story. Good on you for figuring out how to do it. What would you do as the next step if you were to improve on your model? What would you start to explore next?
Oh, I'm glad you asked. Thank you. So one of the key things was that I think this model has a lot more to give. I don't think I've been able to milk it to its full potential. And I think that's mainly being from the fact that I use the smaller data set, which is comprised of 8,000 songs, right? And so for those who don't know, with deep learning or neural network based models, they often like to have larger data sets to work with. They're really good at what they do, but in order to get to that point, they need to have sufficient data. So again, the FMA, the dataset archive that I pulled from, they have much larger data sets comprised of like 100,000 songs. But I wanted to do more of a crisp DM approach and iterate and get like an MVP, a minimum viable product out. And so I ended up working with this data set. But next steps, the immediate thing that comes to mind would be going towards those larger data sets and seeing if I could get better performance out of the same configurations with that.
Excellent. And did you try any other modeling techniques besides what you presented here?
Yeah, so initially what I wanted to do was I wanted to just use the MEL spectrogram. So again, MEL spectrograms are just a visual, I can show it here. MEL spectrograms, this picture on the left, is a visual representation of audio, a frequency of sounds. And so I wanted to use that as my primary resource for training the models. And so I used 2D convolutional neural networks. I found that, for reasons I can't explain, it wasn't working as well. The performance I was getting out of it wasn't as great. And so after trying that, and it takes a lot longer to process 2D convolutional neural networks, I scaled that down to 1D via this process. And then I went to the 1D iteration. So after working on that a little bit and searching online, I found that there are these CNN LSTM hybrid configurations that people use, which have seen results in the audio space. And so that's when I went to my final configuration of a 1D CNN with an LSTM on the back.
Hey, great work, man. I look forward to chatting more after this call.
Thanks, Alex. I mean, it goes without saying, but also if there are any non-technical questions or just questions about anything, I want to reiterate that, like, please ask, because I was a student in the last cohort before I did the program watching these, and I'm like, I don't know what's going on, but it looks cool, so feel free.
To get us started on the non-technical questions, Ken, can you remember what song it was that you showed there in the radar chart at the end?
Okay, so I don't actually have this particular song because I pulled this straight out of my data set, which had the trimmed audio, et cetera, et cetera. But I don't remember the exact track, but I think it was a Beatles song, actually. Because popular audio. But yeah, you could put anything into it and it should spit out an answer.
Thank you so much, Ken. Moving on, our next speaker is Laura Nguyen, a data scientist with 5 years experience in the tech industry. Laura is no stranger to data science. She's worked as a machine learning dataset analyst at Amazon and also as a search analyst in Yahoo. And tonight she'll be talking about preventing sex trafficking by using data science. Laura, take it away.
Thank you, Michelle. Hello, everybody. I will be presenting on how we can use hotel room images to identify hotel chains and prevent sex trafficking. So sex trafficking in the United States is a hidden problem that people know exists, but little is being done to prevent it. It's estimated that roughly 400,000 people are victims of sex trafficking in the US each year. Before I talk about my data set, I want to point out that in 2019, 12 major hotels were sued for their reckless inaction and role in the sex slave trade of women and children, according to Reuters. Hotels are inadvertently profiting off of these crimes, and many victims' images are shared in these hotel spaces. So what if we use hotel room images to train a model to predict what hotel chain that room belongs to? So a little bit about the data. I have 1 million images from a Cornell dataset, which the images were gathered from 2 sources, travel websites and an app called Traffic Cam. And our goal is to predict hotel chains. I've selected 6 chains from the 1 million images. On the right, I have a graph displaying how many images are in each category. So that gives us 14K training images total and 3,500 testing images total. Here we have a few sample images per chain, Best Western on the left and Hyatt on the right. A few more images. Observe that there aren't many obvious patterns or differences that help us detect which chains are which. But there are some locations do have pools and spas and other amenities that might help distinguish them. So how well can a machine perform at hotel chain prediction? Well, my base model received an accuracy score of 24% at predicting the most frequent hotel chain, which is Hilton. And my first model received a test accuracy score of 62%, which is great. However, the test accuracy score is 22%, which indicates that there's overfitting happening. And in order to make convolutional neural network models work better, we must adjust the structure of the model. So to prevent overfitting specifically, I increased the dropout rate and decreased the learning rate. I also increased the epoch size and batch size. And though these seem like easy tasks, the higher the epoch size means that there will be more iterations, and the lower the learning rate means that the test will take longer. The model will take longer to learn, which is good, but it is very time consuming. So Model 3 is fairly low in accuracy score of predicting hotel chains, but it beats the base model and has potential to improve with more epochs and hyperparameter tuning. Although the model isn't quite where I want it to be, it's still pretty amazing that a machine can correctly predict 25% of the time just by looking at the images of hotel rooms. And as I mentioned, I'm looking forward to adjusting the structure of my model by increasing epochs and reducing layer sizes. Additionally, I think that more organized data is helpful, and I'm interested in introducing transfer learning in future iterations of this project. Thank you. Are there any questions?
Yeah, I'm just kind of curious about the work towards making this model, and I understand it's quite a struggle just to get that nice like tuning and everything at the end. So you settle on 10 epochs, and I'm curious, was there a certain constraint, like not having a graphics processing unit or some other thing that really kept you from growing to like 50 plus epochs on this one?
I think if I had 50 plus epochs, I would have had to start weeks ahead of time or a week ahead of time. I know that just 10 epochs, 100 batches took hours.
Wow. Okay. Gotcha.
I hope this is allowed, but I think this is an amazing project. My name is Max Weiss, by the way. I was in the last cohort, so you guys saw me nervously do the same thing 3 months ago. How else have you thought about going about this problem? I know it's very open-ended, but you seem like someone who would have about 12 different solutions and how you're going to solve it next.
Oh, well, I am interested in trying transfer learning, like I said, and I'm really interested, if I had more time, to just add more epochs and keep the learning rate as low as it is. Like I mentioned prior, having such a low learning rate will take a long time for the model to learn. And so you add more epochs, it's going to take 5 ever. So I think that's one of my my top concern if I continue with this.
Hey, I was curious if you decided to augment the data at all. It doesn't seem like a project where augmenting the images would help or hurt you. And then the second question was, did you look at some of the positive data sets and compare, like just looking at them and see if you could see what the difference is, if there were any?
That is such a good question. I love that question. So what do you mean by augmenting the images?
So sometimes, you know, if you're trying to do a cat or a dog, they'll like either rotate the photo, make a shear to it, turn it black or white. It doesn't seem like a data set where that would make total sense to me. I was just curious if you had done it or not.
I did nothing only because there were 1 million images. But I think that this data set, as vast as it is, could still be organized, and there still could be more images per category. Some categories or hotel chains have 600 images, whereas bigger hotels have 4,000 images, and that's really imbalanced. Oh, and also the original data set had human masks to replicate real world, victim images. I would love to introduce that just to better represent those images.
I'm just kind of curious as well, just on how hard it was to train this model. What was your optimizer? Did you go with the standard Atom?
I did, yes.
Okay, gotcha. Okay.
Sorry, one last question on the corpus of data here. I missed how you got your data. Are you pulling from videos at all by chance and doing screen caps?
No, they're just images from Traffic Cam, an app, and like TripAdvisor, like travel websites.
Okay.
So I get a mixed bag of images. Sometimes it's pictures of food. Sometimes it's, people like to take pictures of their food for some reason. And sometimes it's nice room images. So that's why I was saying I think this data would be better off. It was clean better.
Yeah, it's a tough problem. Great job on it.
Thank you.
Can you speak some more about why exactly it is such a tough problem, Laura?
Why is it such a tough problem to work with this large data set?
No, I'm thinking more about like classifying a specific hotel.
Oh, yeah. So earlier I'd shown a lot of images. Looking at just Hilton and Crowne Plaza left and right, you couldn't really, with the human eye, you couldn't tell them apart. It's just a bed or a bathroom. It's difficult. And I think that if we or by category, like room or bathroom or spa, that might help.
Yeah, it seems like hotels are very specifically designed to all look the same, which works against you in this case.
Yeah, but I think still 25% accuracy is pretty darn good for a whole bunch of images of rooms.
For sure. If there are no other questions, we're going to go to our last speaker in this group, which is Nathan Berkeley. Nathan was previously an immunology lab manager and is really interested and very skilled in natural language processing and data pipelines. So his project today is all about detecting astroturfing or people generating fake reviews for companies, which he'll tell you about more, and ways that you can detect that. So here's Nathan.
Hi, everyone. My name is Nathan Berkeley, and this is Identifying AstroTurf Reviews. The problem: fake or AstroTurf reviews have become more common as shopping continues to move online. AstroTurfing is the practice of writing a fake review to inflate the score of a product or service, which compromises data integrity. The data: 700,000 total Yelp reviews. 56% of them were real, 44% were fake. 12% of reviewers were a one-entry spam account. The biggest spammer had over 1,700 fake reviews. 65% of the reviews were fake. And the most AstroTurf restaurant was almost 99% fake reviews, which is insane. So during my first round of modeling in EDA, I tried to do an NLP-only approach, and it wasn't very successful. So following the CRISP-DM process, I did another round of EDA and feature engineering. I kind of wanted to look at if there's, maybe some correlation between total punctuation, different punctuations, word count, sentence count. None of that really helped, but I noticed that funny count, cool count, useful count, rating were potential candidates to add into my model. And I ended up settling on adding in useful count and rating, which improved my model. In terms of the models I chose and my metric, I chose precision because in the real world, that first slide I showed you where it was 99% fake, that's kind of an aberration. Normally you might have less than 10% fake reviews. So I figured in standard fraud cases, you're probably concerned about recall because there's a monetary loss or there's a cybersecurity risk. But for this, the challenge is how can we filter out the bad reviews in a greater amount than we're discarding the good reviews. So with that being said, I tried naive Bayes, random forest, and logistic regression, all with NLP only features the first time. They didn't perform very well by themselves. And the reason for this is that on this data set, most of the fake reviews are well written by people who do this for a profession. So they're smart enough to know, okay, these are more or less some of the vocabulary that have been historically correlated with a fake review, and they've avoided that. Normally when you use an NLP technique, unigrams, bigrams, trigrams are very powerful. In this case by themselves, not so much. Trigrams actually make the models worse, which is kind of interesting. So with that in mind, I pivoted to RNN's GRU and LSTM. It performed a little bit better with GRU at 66% precision and LSTM at 67. That's where I spent the bulk of my time this week, was trying to tune the hyperparameters, get better performance out of that. When I felt like I couldn't proceed anymore with that, I tried to add in those non-NLP features to the second logistic regression model, and that improved it to 68% precision. I wanted to benchmark my model performance versus other groups just because it's a difficult task, so it's kind of nice to know how I compared to other groups. The OT group used to have the best model on the market. We ran a SVM model that used to be the best at 67%. My last logistic regression model was able to beat them by 2%, clocking in at just under 70%. And then Bing Liu, who I got the data from, they currently have the best model at 86%. So they really did an outstanding job. This is an example of what I'm trying to work towards in detecting. This is an example of a very well-written fake review. If you show this to someone, they're probably going to have no idea it's fake. The other reason it would give my model problems is because the useful count is high. And as I mentioned earlier, typically speaking, reviews that have a higher useful count are real. So the person who wrote this did a great job. In conclusion, it is difficult to identify the AstroTurf reviews with high precision using conventional modeling. Adding non-NLP based features such as rating and useful count improves regression. However, in order to deploy the model, it needs to be more precise. So when deployed in an environment where the data is not balanced, as that's usually the case, it can filter out more fake reviews than real reviews discarded. As far as the next steps, I need better domain knowledge. The Bing Liu group spent literally years studying this, and that's how they got good at figuring out the patterns. So I need to investigate the structure of reviews that avoid detection, and I need to enter more meaningful features that help improve model precision. And these are my sources. Thank you for your time, everyone. I'm going to open up for questions, and if there's no questions, there's some interesting details I'd like to discuss a little more that didn't quite make the cut for the presentation.
Nathan, I'd like to ask a question, if I may.
Yeah.
It's a very layman question. I'm just curious as to when you have your data set, the original data set, and you're going to train the data, how do you know which review is fake to begin with?
Oh, that's a great question. So I'm glad you asked that, by the way. So I'm sure Michelle can vouch for this. She's probably tired of me asking, can I do this for my capstone? Because I've been wanting to do this for a long time. And the first time I pitched this idea was I wanted to generate a label myself. You know, not as strictly fake or not fake, but to try and identify, you know, the likelihood of it being AstroTurf. So what ends up happening is one of the other instructors put me in contact with the professor who I got the data set from, and they confirmed with Yelp that these were reviews that were spam. So this is confirmed by Yelp themselves. And that's how we're able to get, you know, a measurement of whether something was actually a fake review or not.
Thank you.
Yeah, no problem. Thanks for the question. Okay, if there's no more questions, I'd actually like to real quick talk about a few things while we have the time. So one of the more interesting things I found, oh, sorry, hold on, let's check the chat. Oh, sorry. It's hard for me to see when they're screen sharing, so I'm just trying to make sure I'm not ignoring a question in the chat. So this bottom line right here, so this restaurant right here, this was kind of interesting. So when I was investigating this, the first thing I thought was, that's kind of interesting that in almost all the reviews, you know, there's a lot of profanity. So the first thing I thought of when I was doing the feature engineering was, okay, maybe I need to check for, you know, profanity count if someone's maybe a less professional reviewer. And then funny enough, it's actually a heavy metal restaurant. So probably, you know, local to that, because when I kind of scanned the rest of the data, that was, you know, where it was mostly concentrated. So that was kind of a funny story. The other thing I'd like to talk about is when you talk about model performance, one of the things that I thought was interesting is what I was trying to do was detect a fake review without using user information. Because if, say, someone has 1,000 fake reviews, that's pretty easy for Yelp or anyone else to figure out, you know what, this is obviously a fake account, we need to ban them. It's very challenging to do on the first attempt. With the research I've done, all three groups, myself included, we actually struggle with that. Even with the best technology on the market, how they modeled it was they would basically take an account that had multiple reviews, and they would look for style differences, like when you talk about your personal writing voice. And, you know, if, say, they had 10 reviews on someone and they notice, you know, the 11th review was in a different state, which is, you know, probably enough to look into it by itself, and it's, you know, a significantly different, you know, personal style, they were able to mark that as spam. And I have a feeling that that's kind of how Yelp, at least part of their model, how they identify it.
Nathan, one follow-up question, if you don't mind.
Yeah, of course.
Was there any attempt made to identify pro or positive fake reviews versus negative? Or is that something that can be done as an extension?
I'm sorry, I'm having problems on my end. Can you repeat that last part? I'm sorry.
Any way to use this model that you've developed to extract information on fake pro or positive reviews versus fake negative reviews?
Oh, that's a good question. I'm sure there is. I would probably have to look at it manually. Off the top of my head, I don't know the code to extract that from the confusion matrix, but that's one of the things to look into, to be sure, just to kind of look into the structure of, you know, why my model specifically is, you know, misclassifying some of them. Like the reason why I use this one is because I can tell you right now without a doubt that this one was misclassified, because there's nothing in here, you know, that I would think would be vocabulary wise that would show up in there. Again, like I said, you know, the unigrams and bigrams by themselves, this is why they fail. And this is crazy, right? That the useful count is so high for a fake review. So that's you know, the real challenge here is, you know, off the top of my head, I couldn't identify the structure, and for a lot of models, they have trouble identifying this. That's why a lot of groups, they look into the stylistic differences between reviews, and that's good. But what I want to do eventually, if it's possible, is to try and, you know, identify a one-off, because one of the things I was interested in is that this line right here, the 12% being, you know, fake one-entry reviews, I'm sure a lot of them are burner accounts or bot accounts, but Yelp has such a robust detection system. I'm almost wondering if they are actually able to catch people on the first try. So that's why I'm optimistic that there's a way to do it. I just haven't discovered what's actually critical. When you look at an NLP set, oftentimes there'll be a lack of features, but there's not a lack of content, right? I think each review, you know, there's over 700,000 reviews. I think each one was about 170 words each. There's not a lack of content. It's just, how can we, you know, accurately find those relationships without relying on an account that has, you know, 5,000-10,000 reviews. That's what I'm trying to work towards. But unfortunately, it's proven pretty difficult.
Last question from me, anyways. Do these fake reviews tend to be either 1-star or 5-star reviews generally?
Okay, that's a great question. That's actually one of the things I looked into. The thing is that the average, so first of all, the average rating, it is a little bit higher for the fake reviews. Overall, though, there's actually a lot of 4-star fake reviews. But as you said, though, not that many 2-star fake reviews. Normally when it's a fake review, like you said, typically it's a 1 and a 5. This data set didn't show the disparity I was thinking of. My last project where I worked on investigating NLP with Amazon ratings, it's exactly like you said. There was a huge disparity where it was, 5-star reviews was more than 60%, 1-star reviews was in second place. So that was probably one of the most surprising parts about this, was that it is a little higher, the percentage of 5-star reviews and 1-star reviews, but it's not as big as you would think, because one of the things when I read Bing Liu's research was that some of the best fake review companies, they charge you per star. So maybe I'm off base here, but they could have very well bought 1,000 reviews for at 4 stars because that was cheaper. That's something that they mentioned. So maybe that's why the discrepancy wasn't as big.
Thanks, Nathan. That's really interesting to hear. Not just how the text of the review is important, and also the specific features like the number of stars that it has. Joseph here points out in the chat, it probably costs more to get the 4-star fake review instead of a 3-star fake review if you're paying by the star. But also user features that are involved in that, such as how many times they've posted. That brings us to the end of this particular rotation, and we'll be going back to our first speaker, who is Kelly. So if you've been here from the start, feel free to jump to a different room at this point. Feel free to stay if you really enjoyed these and you want a second time around. But we'll just give people a moment to switch rooms, and then we'll be going back to Kelly again.
Great job, everybody.
Yes, same. See you.
See you.
We're almost through the first hour. We're going all of 2 times.
Yeah.
I just say
some great questions. And for those in the room, again, feel free to come off mute and ask questions after the talks. Ask questions into the chat at any point if you feel worried that you'll forget about your question by the end of the presentation. And then we'll start up again with Kelly. If you missed the introduction at the beginning, Kelly has been in the tech industry for a few years. She's worked as a program manager and a consultant, and has a degree in statistics from Cornell. And she'll be talking about using LSTMs to predict humor in reviews. Kelly.
All right, thank you, Michelle. Go ahead and share the screen. All right, everyone can see it okay? Nice. So today I'm going to share some of my findings on my quest to detect humor in Yelp reviews using LSTMs. The LSTMs are a special type of recurrent neural network that take into the account of sequences, or the data that has an order to it, which is why I thought it would be the best sort of model to use for this project. So going into this project, the question I asked myself was, how can we best detect humor in text data? And I was interested in answering this question because of the interesting applications in building AI systems such as chatbots and virtual assistants, which if we were to identify and inject humor into conversations, that can enhance overall user experience. And in order to, the methods I use to try to answer this question involve natural language processing and deep learning on the Yelp Open data set. So a look at the data and shows that there's about 8 million total reviews, and each review has a funny attribute corresponding to the number of votes that review has received. The distribution of the funny votes is actually very skewed to the right, which led me to choose to turn this into a binary classification problem of funny versus not funny. And I chose to define funny as having 3 votes or more to account for noise in 1- and 2-star reviews, which gave a total of about 340,000 funny reviews and a 4% of the funny class. So before modeling, I had to process the text to get into the proper format, first fit a baseline logistic regression to get a sense of what a simple classification could look like. That process involved cleaning the data, tokenizing it, and performing a TF-IDF factorization, which is essentially a way of representing words with counts. For the LSTMs, the process was a little bit more complicated. It also involved text cleaning and tokenization, but I also had to create sequences and then pad the sequences up to a certain length. I chose about 200 words because that's around the average review length in order to fit the same length sequences into my models. So after some fiddling around with the architectures, I decided to compare 4 models. The first one was the baseline logistic regression. For the LCMs, I chose one with 1 layer of 100 memory units, one with 2 layers of 100 memory units each, and a bidirectional layer of 50 units looking in both forward and backwards directions to take account into take the sequence of words into account in not just the forward direction. And the results of my modeling show that the precision stayed pretty flat throughout each of the models, although the recall did manage to get bumped up about 4% from the baseline. A way to interpret these numbers is that compared to the 4% of the funny class, 10% precision means that this model is doing 2.5 times better than just pure chance. And the recall is, the higher the recall means that the less false negatives there are. So that if a review is surfaced as funny, it is actually going to be considered funny. Seen another way, the results show that although the bidirectional LSTM had the highest recall, the LSTM with 1 layer or the LSTM with the simplest architecture actually was able to reduce false negatives the most, which is what we wanted because of our use case. And so some final thoughts from this study. I found that humor is heavily context dependent, which is probably not surprising. By fitting the bidirectional LSTM, I was able to confirm that signals of humor can be given by surrounding words in both directions, not just forward. And adding more complexity through layers and more than one direction slightly improved the performance. But in the end, a simple classification model may suffice, especially given time constraints, because the logistic regression performed very comparably to the more complex LSTMs. As for next steps, I would like to try to boost my results using transfer learning with the BERT model that Google came out with in 2018. This model was trained on a very large corpus of words from Wikipedia and Books corpus and contains about 110 million parameters, making it very robust. And in order to get a better sense of maybe how the model is doing in more advanced contexts, such as humor generation, I would like to create a humor text generator from the best fitting model. And now I'll open it up to any questions.
Katie, we've got a question in the chat. Did you try running your model on any text outside of your data set of reviews, such as emails, chat, and so forth? Did it detect funny?
I did not. That would have been a good next step to do. I did find a pretty interesting data set that had sarcasm labels, and I think that would have been a nice thing to use using a similar LSTM architecture, because the nature of the problem would be similar enough to apply the same sort of tuning and hyperparameters.
Thanks. And for those of you who have just joined us, feel free to come off mute and ask a question, or put your question in the chat if you can't speak right now. Some old faces here, Shankar, Jamal, it's really nice to see you. I hope you're enjoying the presentation so far. Kelly, for those in the audience who don't have a data science background, what is TF-IDF factorization?
I'm glad you asked, because I definitely prepared an appendix for this. So TF-IDF basically takes into account the frequency a word appears within a certain document, in this case reviews, but it also takes into account how many other documents that term appears in. So if it's a stop word such as that appears very frequently, we don't want to give it more importance than it should. So TF-IDF assigns a numerical statistic based on the relative importance of a given word, taking into account these two numbers.
So why is that important?
So that should give information on how important this word is to a review, so that when it's fed into the model, we can see, so it provides a numerical representation of the word, because the model can't take text itself. And the representation obviously is kind of simplistic, but it sometimes can do a very good job, as was shown by my logistic regression. So.
Thanks. And I appreciate that what we're seeing here tonight is the final product. What were some other things that you tried that maybe didn't work out so well, or obstacles that you faced along the way?
Mm-hmm. Well, the biggest obstacle was probably trying to get everything onto AWS. There was definitely a moment of irony where I was like, I was doing this project on humor and nothing about this process is funny. But yeah, if that had been successful, I would have loved to do transfer learning to see if a more robust model would have performed better on a data set like this that happened to be very unbalanced, and potentially use different types of data sets, kind of like the sarcasm data set that I mentioned.
Yeah, I think sarcasm would be really cool to see, and has interesting aspects like humor where it's very context dependent. Perhaps even more difficult because the intent can be so different from the words.
Right. Exactly what I was thinking.
Any other questions from the audience? If not, thank you so much again, Kelly.
Thank you.
Okay. Next up is Ken Shrivastava. Ken has a background in materials and industrial engineering and a passion for music on the side. And so tonight's presentation is all about using different techniques for music genre classification. Shankar, you might be especially interested to see this, because this might remind you a little bit about Nick's project, where he tried a similar thing. So you can compare the two. Ken.
Thanks, Michelle, for the introduction. I hope I don't disappoint. Let me share my screen here. All right. So yeah, again, hello, everybody. My name is Ken Shrivastava, and today I'm going to be presenting to you on music genre classification. More specifically, predicting song genres using raw audio via deep learning models. So jumping right into it, a little bit about the workflow. So again, I'm processing raw audio here. And so the first thing I needed to do was restructure my data. It's unstructured, unwieldy, and so I needed to store the audio files in a way that could be accessed via scripts, Python scripts. So I did that first. And then I took the audio and I converted it to MEL spectrograms. And MEL spectrograms are a visual representation, an image depicting that same audio, because my models need an image in order to train on them. And so I later found in my project that converting the images even further into one-dimensional data yielded better results for me, so I did that. And some of the other parts of the process that went into my project are doing EDA on the metadata associated with that, eventually transitioning all of my pre-processed data into AWS for the next step being modeling and building out my models, and finally deploying the best model that I was able to create on a web app. So that's a little overview of what we're going to do, and I'll talk a little bit more about some of the details. So the data set, it's from the Free Music Archive. In the field of music information retrieval, this is a very popular data set. The one that I'm using is their smaller data set. It's comprised of 8,000 songs. Each of them is trimmed to just a 30-second snippet, and they're equally split, so 1,000 songs each across these 8 different genres. The data set's a little bit sparse. While you have all of the audio files here, the metadata associated with it, i.e. like the genre itself, or the date that the song was created, the composer, the artist who made the song, that information's a little bit more sparse and less available. So going into my EDA here, EDA short for exploratory data analysis, just looking at my data, studying it a little bit, the most interesting finding that I was able to gather was tracks per year per genre. And so this graph's a little bit noisy, but the key takeaway that I want you to get from this is that we can see over the course of this 10-year span, roughly from 2008 to 2016, that all of the genres have the number of songs from each year distributed fairly evenly, barring this outlier with instrumental having a majority of its songs from 2015. All of the songs are fairly evenly distributed across this decade. Now, what that means for us is that hopefully when we train a model off of this data, it will be more robust, because if there's any trends that are changing over time with different genres, it'll be more robust and be able to better tackle those because it has a wide frame of reference. So jumping right into it, for the sake of brevity, I'm showing the final model that was the most performant for our use case here, determining genres. And so the final model that I ended up using is a CNN LSTM hybrid configuration. So the first 3 layers here are comprised of separate convolutional 1D neural networks. And so what these are doing, it says feature extraction up here, is they're trying to depict little pieces or elements of the song, like such as a single drum hit or a guitar strum. And they're slowly picking up in size, and they're getting larger and larger features until finally we feed that process data into the LSTM layer, which is taking that process data and hopefully looking at longer temporal trends in the music. So trying to identify, again, in layman's terms, things like rhythm, cadence, beat, that will help inform the machine learning model on what type of genre this song might fall into. So coming now to the performance, again, of this final model configuration that I ran with, we can see that, okay, the baseline model that I started with had roughly 12.5% accuracy. This makes sense because we're predicting out of 8 genres. So if you're to choose randomly, the likelihood of you getting it right is about 1 in 8, 12.5%. And so from that baseline, with our final model configuration, we were able to improve the accuracy of predicting the song genres up to 49.3%, which is about a 37% increase in performance. Worth noting, I chose accuracy. For those uninitiated, there are many different metrics by which you can optimize your model. I chose specifically to go forward with accuracy because we don't particularly care about it picking one genre over the other correctly. We want it to be able to accurately predict all genres equally well. So there is no reward or penalty, for doing one better or worse. So we want to see them all do well. And finally here, just very simple demo, but I'm developing a web app that takes my final model, and you could upload your own audio, and it will take that audio and process it and generate a radar chart. And so a little bit more fun and interactive. You can provide your own audio, and it will take that audio, pre-process it through all the steps I mentioned earlier, and try to determine, again, which one of those 8 genres this song falls mostly into. In this example case here, we see that it's very highly likely that this song is a folk song, maybe with some rock influences in it. And I think with that, I open up to questions.
Thanks, Ken. I noticed that you were using one-dimensional CNN layers. Is that common? How did you decide to do that?
Great question, Tomas. Thank you. So let me see. Would it be better to go back to? Well, let me take it to this. So this is, I didn't get to fit it into the presentation, but this is that MEL spectrogram I was talking about. Now, I mean, to most of us, myself included, it doesn't look like much, but it is a visual depiction of the audio of a song. And so the way convolutional neural networks work, it's complicated, but in short, it parses through pieces, chunks of the image, and tries to discern patterns out of those chunks. And so in doing this, there's kind of a spatial element that's present when it's looking at the image. And so it might look locally at the high frequencies in a song, maybe like whistles or like really high vocals, but it won't at the same time look at lower frequencies, such as like a bass guitar or a tuba. And so I didn't like how the model was interacting with the data, or at least what I speculate the model was working with the data. So I converted it into one-dimensional data by breaking the image of the audio down into frequency ranges. So for any musicians, you might know, again, like certain instruments typically reside in certain frequency ranges. So I did common breakouts like, again, vocals, whistles, bass guitars, tubas, wind instruments, brass instruments. And I took these slices of frequencies and I compressed them down by averaging them. And this gave me 7 one-dimensional input channels, which I was then able to use the 1D CNN for. Now, to Tomas's question, the purpose of doing this is so that instead of looking at these little windows, which might not give the whole picture for any given time increment, by flattening this into 7 channels like this, it can look further out. So it can look more over time. So hopefully the model will be more informed about looking again for those temporal trends, which the LSTM is looking for. So, I mean, at least with my configuration, it did seem to be more performant. So this did in fact yield a positive effect on the final result.
On that, are there other features that you think that you could add to the model to improve performance, Ken?
So interestingly enough, like since we're dealing with raw audio here, it's again, unstructured data, it's less nice to work with. I think for my use case, again, I guess I didn't discuss it too much, but the intent of this is to be able to classify genres. And if you even go even more broadly, classifying audio, music information retrieval, it's a whole space, a whole field of study in and of itself. And so at its core, the purpose of this project was to be able to classify raw audio. You could, again, apply filtering or do transformations on it, but I'm trying not to give it other features to work with in case someone only has a raw piece of audio. That being said, if you did want to provide, feature data, I did a previous project using audio features, so not actual audio, but information about the audio to, again, do genre prediction. So you could supplement this model and add something to that effect to maybe help inform its decision. But that would be a decision path for you to decide what you want this model to do for you.
Thank you. That's really interesting to hear those possible next steps or other pathways to explore.
Yeah, I do want to mention, so it came up organically last time, but if anyone's for some reason interested in CNNs or LSTMs, I think that this model, even though it only got, I think, like an accuracy of what, like 49%, I don't think that that's fully indicative of its performance because the model was only trained on 8,000 songs. And it's important to note that neural networks in general, deep learning models, they're very highly performant, especially compared to other forms of supervised learning. But their biggest thing is that you need a lot of data in order to train them. So 8,000 songs might sound like a lot, but especially if you only have 1,000 songs per genre, if you could feed it more data, it could probably depict more trends out of that and predict more accurately. So I think that, again, for next steps, there's a lot of upside potential for this model in its same configuration if I were to supply it with more data.
Thank you very much, Ken. Then if there are no other questions, we're going to move on to Laura. Laura Nguyen has over 5 years experience in the tech industry working as a machine learning data set analyst at Amazon and a search analyst at Yahoo. And she's talking tonight about a very serious topic, which is how can data science help to prevent sex trafficking in hotels? And in particular, can we use image recognition techniques to be able to identify certain hotels? Laura.
Thank you, Michelle. Hi, everybody. As Michelle said, I will be presenting on how we can use hotel room images to identify hotel chains and prevent sex trafficking. Sex trafficking in the United States is a hidden problem that people know exists, but little is being done to prevent it. It's estimated that roughly 400,000 people are victims of sex trafficking each year in the United States. Before I talk about my data set, I want to point out that in 2019, 12 major hotels were sued for reckless inaction and having a role in the sex slave trade of women and children, according to Reuters. Hotels are inadvertently profiting off these crimes, and many victims' images are shared in these hotel spaces. So what if we use hotel room images to train a model to predict what hotel chain room that it belongs to? So a little bit about the data. I have 1 million hotel room images from Cornell, which was gathered from 2 sources, travel websites such as TripAdvisor and an app called Traffic Cam. And our goal is to predict the hotel chains. I've selected 6 hotels from the 1 million images. And on the right, there's a graph that represents how many images are included per chain, which gives us a total of 14K training images and 3,500 testing images. Here are a few samples of the images per chain. Best Western on the left, Hyatt on the right. You can observe that there aren't many obvious patterns or differences that make these hotel rooms unique. Although some locations have pools, spas, and other amenities that do distinguish them. So how well can a machine perform at hotel chain prediction? My base model received an accuracy score of 24% at predicting the most frequent hotel chain, which is the Hilton. My first model received a test accuracy score of 62%, which is great. However, the test accuracy score is 22%, which indicates to me that overfitting is happening. In order to make convolutional neural network models work better, we must adjust the structure of the model. So to prevent overfitting, I increased the dropout rate and decreased the learning rate. I also increased the epoch size and batch size. And these seem like easy, minute tasks. The higher the epoch size means more iterations, and the lower the learning rate means the longer it will take the model to learn, which is good, but it's very time consuming. Model 3 has a fairly low accuracy score of predicting the hotel chains, but it beats the base model and has potential to improve with more epochs and more hyperparameter tuning. Although the model isn't quite where I want it to be yet, it's still a pretty amazing model machine. It's still pretty amazing that the machine can correctly predict 25% of the images just by looking at the hotel room images. As I mentioned, I'm looking forward to adjusting the structure of my model by increasing epochs and reducing layer sizes. And additionally, I think more organized data is helpful, and I'm interested in introducing transfer learning in future iterations of this project. Thank you. Are there any questions?
Laura, I wanted to ask you what the most unexpected thing or unexpected challenge was during this project.
Thank you for asking me that. I've been thinking about this a lot. When I picked this project, I was really interested and excited about it. I didn't realize how difficult it would be to extract the images and work with the images. Like I'd mentioned, some of the hotel chains have, don't have as many images as others. So Hilton is the highest with 4,000 images, while there were other hotel chains that I was interested in looking at only had 600 images, and that wouldn't have really worked well for me. And working with AWS was a nightmare. So I had to work with all of these images locally.
Nora, what would you do to improve this current model that you've got further in terms of trying different architectures, trying different hyperparameters, if you had more time to play with us?
That's a good question. So this graph here shows me that the lower learning rate is pretty useful. I think I want more epochs, but that will take a longer amount of time. So I think I'm going to keep it the same as I have here, just increase the epoch size and just let it run and see what happens.
And I'm curious, you said you had photos from 2 different sources, the traffic cam and then the travel reviews. How do those images differ? Do you know?
No, I can't say that I do. I combine the 2 images, but I do know that travel websites will have a more mixed variety. Some of them have been altered to look better for the websites.
Yeah, somehow it never quite seems the same in real life as those beautiful glossy images that you see on the web. So I'm sure that's something to take into account if you're getting images from different sources, especially as I imagine some of these images might be coming from hidden cams. So other sources that are very different from those picture perfect travel images.
Yeah.
Any other questions from the audience? All right. Then up next is Nathan Berkeley, who's been looking into astroturfing, detecting astroturf, so in other words, like fake reviews. Nathan has a background as immunology lab manager and is particularly interested in natural language processing. And I think he's really done well in examining a few different techniques for data pipelines for natural language processing in this capstone. So, Nathan.
Hi, everyone. My name is Nathan Berkeley, and this is Identifying AstroTurf Reviews. The problem. Fake or AstroTurf reviews have become more common as shopping continues to move online. AstroTurfing is the practice of writing a fake review to inflate the score of a product or service which compromises data integrity. The data. 700,000 total restaurant reviews from Yelp. 56% of them are fake, 44% are real, and the biggest spammer had over 1,700 fake reviews. 65% of their total reviews were fake. The most AstroTurf restaurant had almost 99% of the reviews being fake, which is insane. So with my first round of modeling in EDA, I focused solely on NLP. NLP techniques by themselves proved mostly fruitless. Typically, when you have an NLP project, having unigrams, bigrams, trigrams, basically building a common vocabulary among classes is a very powerful tool. Not so much for this project. So what I did was I did a second round of EDA and looked at the feature correlation with the target to see if there would be any possible candidates to add into my model. I feature engineered some different counts and punctuations to look in if there was any relationships there. What ended up happening though is I noticed that funny count, cool count, useful count, and rating were all potential candidates. And out of those, useful count and rating ended up being important to helping my model. In terms of the models I chose and the metric I chose precision. Typically speaking, when you do a fraud, not fraud type of scenario, you're interested in recall because you want to minimize potential fraudulent occurrences that slip through. It could be a monetary loss. It could be a cyber attack. In this case, in most scenarios, you have much more real reviews than fake reviews. So you want a model that's precise enough that it'll be able to correctly identify them, because if you're discarding more good reviews than you are fake reviews, you're just further diluting the data, which is what we're trying to correct. So the baseline model is just a 50% guess. And then after that, I experiment with naive Bayes, random forest, and logistic regression, all with NLP only features. None of them performed very well. Logistic regression was the best of them at about 61%, at which point I pivoted to GRU and LSTM recurring neural nets. GRU performed at about 66% and LSTM at 67%. That's where I spent the bulk of my time, was trying to tune the hyperparameters for the LSTM. I think long-term this has the most potential. Currently though, my logistic regression with the added features is performing the best at just under 70% precision. I wanted to benchmark my model's performance versus other groups. The AUT group used to have the best model on the market for this using an SVM technique. My logistic regression outperformed them by 2%. However, the Bing Liu team, which I got the data set from, they currently have the best model at 86%. And I wanted to show as an example what I'm trying to work towards long term. This is an example of a well-written fake review. When you read it, there's nothing that's going to be, obvious in terms of vocabulary that's going to be in fake, not fake. It's probably going to be in both classes, so you're not going to be able to mark it with just that alone. And this right here, the fact that the useful count is very high, that means that, a lot of other people thought that this review was real as well. So they did a good job writing this. This would be very tough for my model to detect. In conclusion, it is difficult to identify the AstroTurf reviews with high precision using conventional modeling. adding non-NLP based features such as rating, useful count, improved logistic regression. However, as I mentioned, in order to deploy the model, it needs to be more precise when deployed in an environment where the data is not balanced. So that way it can filter out more of the bad reviews than we're discarding the good reviews. And then for the next steps, as I mentioned earlier, I need better domain knowledge. So I need to investigate the structure of the reviews that avoid detection. That's how the Bing group did so well, is they've literally spent years researching this as a team, the different patterns. So I think that's the next steps for me. Special thank you to Bing-Lu and the team for the data set. Thank you for your time. I'm going to open up for questions. And if there's no questions, there's a couple of things I'd like to talk about a little more that I found interesting during the course of my project.
I have a question, Nate.
Mm-hmm.
So you mentioned that you would want to further investigate LSTMs, which, at least for my project, I only use text data. How would you incorporate some of your numerical features with your text data?
Okay, so that's a good question, and that's one of the topics that I wanted to try but ran out of time. So hopefully if I can get my AWS approved, because there's been kind of a hitch in that, I would like to transfer to AWS first of all to scale up. And when incorporating the numeric features, when you add it to a sparse matrix for, the supervised model logistic regression, that's actually fairly easy. There's a built-in that helps you do that. With the LSTM, it's a little more complicated. As I understand it, you are adding it into a dense layer later on. So the reason why I didn't try it now was because I ran out of time, but I'm definitely interested in seeing if that helps, because those two features by themselves improve my model by 8%. So if that could push me to, even if it's not linear, if that could push me to, in the 70s, that'd be nice for a short-term goal.
Great, makes sense.
And Nate, you spoke about LSTM and GRU models. What's the difference between those?
So I'm not an expert on the GRU, but as I understand it, they combine the input and the forget gate, so there's less parameters, whereas LSTM has them all separate. Yeah, so basically with an LSTM, we have this cartoon here. Essentially what's going on with an LSTM is you have your cell state on this conveyor belt, and you're basically making, different adjustments as it's going before you output it. The oversimplified version is that, the first thing you have to do with an LSTM is you have to decide what you're gonna, forget, so you don't overfit the model. So that's one of the things. The second step is the model decides with probability, what we want to keep. Third step is input. Fourth step is the output. With the output, it really depends on what your problem is. For me, it's binary classification. My target is, fake, not fake, which gets converted to a binary 0 or 1. So in my case, I use sigmoid activation. If you have multi-class, you probably have to use a softmax. So that's the very oversimplified version, but you're essentially able to modify it as you go. And something I didn't touch on, but I tried, was there's a couple ways to build an LSTM. So you have memory nodes, and you can play with them as one of your parameters to see how well it can learn it. You can, increase it, decrease it. Sometimes it's simple. I know some people for non-text projects have gotten away with as little as 3. I found for at least so far, 50 has been optimal, and 100 not only increase computation time, but decrease performance. I also tried doing to stack the layers. That didn't help either, but it was something interesting worth trying.
I have a question for you, Nate. Can I?
Mm-hmm.
So this is kind of more of like a gut feeling type of question, but your data set has been working out of Amazon-based reviews, right?
This one is actually Yelp. That was my last capstone. I was Amazon.
So yeah, okay, if you're working in the domain of Yelp, if you were to take your model and test it in another domain, Amazon, any other website, a movie reviews website, do you feel that the performance would be very different, or what do you think?
So this is strictly gut feeling, and I can't prove it with certainty without testing it, but I would say that Yelp is definitely the hardest data set to train on, because Yelp reviewers, they have an incentive to do good. You become Yelp elite, so they take it a lot more seriously. Amazon reviews, in the last in the last section, you know, someone asked a question, is there a difference in the star ratings? When you look at Amazon reviews that you would perceive to be fake, it's a lot more apparent that they're 1s or 5s. With Yelp reviews, you know, good reviewers that write these fake reviews, you have to pay them per star. So it's a little harder to, you know, tease that out with just the ratings as well. So that's definitely something worth looking into. But for me, my thinking is, if I can build a model on the hardest data set, we should be able to bring it to other data sets and use it.
There's a question in the chat, but I wanted to point out briefly, I wonder what it would be like if you used Kelly's funny data set of Yelp reviews on here. There probably wouldn't be any funny fake reviews, huh?
Well, so interesting story real quick. So funny, I actually dropped. One, because it doesn't help model performance. Two, it actually would invalidate the model because it was really highly correlated with useful reviews, so I had to cut it. So it was fortunate for me that it ended up not being helpful. Cool reviews was extremely correlated with useful, which was interesting that, okay, maybe it's because if someone was willing to put for one, they'd be able to put for the others. But yeah, cool and useful were pretty highly correlated. So that obviously had to be dropped too.
Thanks, Nick. Then there's a comment and a question in the chat. Speaking about Amazon reviews earlier, Alexi IMAX says Amazon is definitely under attack by these types of reviews too, for sure. I mean, there are many applications here, right?
Yes. So Alexi, sorry for not seeing your message. I have to pull up the chat separately. So actually, and Michelle can attest to this, I actually tried originally to do this on an Amazon data set. The problem is that all of the Amazon data sets I got were not labeled. So for one of my capstones, what I wanted to do was I wanted to look at, you know, the difference in rating distributions over time and trying to label it as this is how likely I would think a product has been astroturfed. But the couple of problems, one, there's no way to confirm my theory because it wasn't explicitly labeled. Yelp explicitly labeled these, so we can confirm. And their machine learning, you know, models are very robust, so I trust them. And then two, identifying a product that's astroturfed is good, but like, for example, let's go back to this first slide just real quick. So this right here is an anomaly, right? So with this restaurant, you could probably go ahead and just throw this one out. Like if I had a feeling that, you know, 99% of the reviews are fake, I'm probably not going to go there. But if you had, you know, a product with 10, 20% fake reviews, it's easier to have an idea whether the product's good or not if you can filter them, rather than just blanket saying, you know, hey, this product's been astroturfed, I'm not going to look into it anymore. So that was my reasoning for trying it this way. But you absolutely could apply this to an Amazon data set if you could get a proper labeled data set. It's just that I don't know if Amazon confirms them. So when the Bing Group worked with Amazon, one, I trust them because they've been doing this for 10 years now. But two, I think they already had a better idea of what was going on. Because what they do is they basically look into, sorry, mention number of reviews per reviewer. Yes. So, okay, that's a great point. So, Alexi, I was trying to identify it without using the reviewer ID. The reason why is because if you can identify on the first try, that's, you know, you have a pretty robust model. The problem is that it seems like Yelp might be able to do it, but between the three groups I have listed here, all three of our models actually struggle. If you were to give any of our models a one-off review, it would be really hard to predict. So what the Bing Group did was they would basically take, you know, people that had multiple reviews, whether it was, you know, 5, 10, whatever, and if there was a, you know, a stylistic difference in how they wrote their review compared to the other 10, they would mark it and investigate it. And then, like I said, Yelp confirmed that they were fake. So that was one of the ways to. So you absolutely could look into, you know, if someone was more likely to commit a spam review and then they were banned for it. But I was trying to build a model without the use of that.
So Nate, that was why you tried a model with and without number of reviews, so that you can possibly detect a fake review on the first review shot when you don't have that information about how many reviews this person has had?
Yep, I want it to be agnostic for this model, but yeah, you absolutely could do that. I have a feeling that Yelp can do that as well. Because another thing, this is a little off topic, but when you're when you're Yelp, you can also map it to someone's IP. So this is something I've read where sometimes when people have a bot account, they're too lazy to change, their VPN or, switch their IP. So that's another detection method, but that's something that would take a lot of time to mine. So I didn't consider that. Did I answer your question?
You definitely answered my question. I don't know if there's any other questions from the audience. If not, this brings us to the end of our loop. If you've been here from the start with Kelly, so feel free to move rooms if you'd like to switch and see some of the other presentations this evening. And then in a moment, we'll start with Kelly Zhao again. All right. Then, sticking with the topic of reviews, Kelly Zhao will be speaking about detecting humor in Yelp reviews. Now, Kelly has a few years of experience, both as product manager and consultant, and a degree in statistics. And this background has helped her a lot, both in her time here at Galvanize, but also digging into this difficult topic of how do you detect reviews when that seems so context specific? Kelly, tell us more about that.
Forgot to unmute myself. Thank you, Michelle. All right, I will do my best. So today I will talk about
we don't see your full screen. Oh, there we go.
Okay, can everyone see it now? Great, thank you. So today I'm going to share some of my findings from my quest to detect humor using LSTMs. LSTMs are a type of recurrent neural network that take in sequential data, which I thought was fitting for the nature of humor. So a bit of background. I wanted to know how we can best detect humor in text data. Because humor detection has interesting applications in building AI systems such as chatbots and virtual assistants. If we're able to identify and inject humor in conversations, it can enhance the overall user experience. And I sought to try to answer this question using natural language processing and deep learning methods on the Yelp Open data set. So a look at the data. It contains about 8 million total reviews, and each review has a funny column corresponding to the number of votes a review has received. As you can see, the distribution of the funny attribute is heavily right skewed, which led me to turn this into a binary classification problem of funny versus not funny. I then chose to define funny as having 3 votes or more because of noise in 1 and 2 vote reviews, which gave me about 340,000 total funny reviews, or 4% of the funny class. So before I could do my modeling, I did some text processing to get the text data in the proper format. I first fit a logistic regression as a baseline model on a simple TF-IDF vectorization, which is essentially a word count representation of each word. For the LSTMs, I followed a similar process of text cleaning and tokenization, but then I had to turn the words into sequences and pad sequences up to a certain length that I played around with, which ultimately decided on 200 words per sequence because that was about the average length of a review. As for my modeling, I ended up with 4 models for comparison. The first was the baseline logistic regression, and for the LSTMs, I had one with 1 layer with 100 memory units, one with 2 layers with 100 memory units each, and a third with a bidirectional layer, which was 50 units in both directions instead of just the forward direction. The results of my modeling showed that the precision stayed roughly the same, although the bidirectional LSTM definitely bumped up my recall about 4%. And the way to interpret these numbers is that if someone were to just guess if if a review were funny or not, there would be a 4% chance of them getting it correct based on the distribution of my data. And the precision of these models does about 2.5 times better than that. The recall, so the model is detecting about 10% of the reviews that the model is detecting as funny are actually funny. And the recall is what percentage of those are being returned. Seen another way, the results show that while the bidirectional LSTM had the highest recall, the LSTM with the simplest architecture or with one layer actually performed the best in terms of reducing false negatives, which in this case is what we want because we don't want to accidentally miss a review if it is actually funny. And this leads me to my final thoughts. By fitting a bidirectional LSTM, I was able to confirm that humor is in fact heavily context dependent, as signals of humor can be given by surrounding words in both directions, not just the forward direction. And although I tried to improve my models by adding more, although the models improved slightly by adding complexity, it did take a long time to train the more complex models. So in some cases, a simple classification model such as a logistic regression may suffice, as this produced pretty complicated results. As for next steps, I would like to try boosting my results using transfer learning with the BERT model, which is a pretty famous language model that Google came out with in 2018. This was trained on a large corpus of Wikipedia and books corpus data and contains over 100 million parameters, making it very robust. And I imagine it would do well on very unbalanced data like the data set I worked with for this project. I'd also like to create a humor text generator using the best performing model to see if in fact the text that is being predicted as funny is funny. And with that, I would like to open it up to questions.
I have a light question, just because I'm genuinely curious. What attracted you to this project? What were you hoping to find from it?
So I think I definitely want to do something with text data because that's something I've always had an interest in. I feel like sentiment analysis is done has been done a lot of times. And so I wanted to do something that was similar to sentiment analysis, but was maybe had like a layer of additional complexity. And so humor detection seemed like something that would fall in that domain, but is a little bit more difficult because it's so subjective and hard to define. And so that's, and the Yelp data set was a good data set to work with for this project because it had a very well-defined funny column. And if I wanted to expand upon this, I would probably want to look for data sets that maybe didn't have that column and do some like topic modeling to see the text come up with different hidden topics of humor and see if that would change my results.
Were you able to figure out what were the top funny words?
I did not get around to doing that, but that's definitely something on my next steps list.
And Kelly, I'm interested to know, you said earlier that you didn't want to miss any funny reviews. Why is that?
So since the use case is to detect humor, we want to make sure that if the model is labeling something as funny, we want to make sure that it is being returned and that it's not actually a false positive. That we're not missing false negatives. Yeah, we're not missing any funny reviews if they are actually funny, because then we wouldn't actually be serving the expected result.
So trying to bump up as many reviews that are funny as you can, in case that brings more traffic. Cool. Thank you. Any other questions for Kelly?
Yeah, I do. So Kelly, have you given any thought to trying another round of supervised learning with random forest or naive Bayes? I know those are some pretty powerful text classifiers that might be worth exploring.
So I actually did do that for the, preliminary version of this project. I fit a logistic regression for that one as well, and used naive Bayes, random forest, and we used gradient boosting on just the TF-IDF matrix. And that turned out to be okay. The gradient boosting took a pretty long time, but I ultimately and it did like pretty well, but ultimately went with the logistic regression as the baseline for this project because I figured it was, it performed the best and it would take the least amount of time to compare to more complex model like the LSTMs.
Thank you for answering that. Yeah, that makes sense.
Thank you.
Thanks so much, Kelly. And then we'll move on to Ken Shrivastava. Ken has a background in materials and industrial engineering. And tonight's project is looking at something a little bit different. This is all about music and being able to detect music genres from the audio. Ken.
Perfect. Thank you, Michelle. Let me get my screen sharing going here. And alrighty. Hello, everybody. Again, my name is Ken Shrivastava, and today I'll be talking to you about music genre classification, more specifically using raw audio and predicting the song genres from that audio using deep learning models. So a little overview of my project and the process that went into that. So audio, if you've predated streaming services, you'll know that you used to have MP3 files and things of the like, and you'd have to kind of store them yourself. And so in the same fashion, I have a lot of MP3 files that I used in my data, and I need to store them in a way such that I can access them efficiently for the code that I would use later. So my first part of the process was restructuring those directories that hold that information. And so in my project, I used convolutional neural networks, which I'll talk more about later. And those deep learning models traditionally are used for image classification. So the first thing I did was I converted this audio into MEL spectrograms, which are visual depictions, images that represent that same audio, that same sound. And later, while iterating through the process, I found that even beyond images, it would be better for my models to convert those images, those MEL spectrograms, into one-dimensional data, which again, I'll touch upon later. Beyond that, we do some EDA, again, examining the data a little bit more, getting to understand it a little bit better, and we transitioned our data to AWS for a lot of the modeling portion of our project. And finally, once we had our best working model, we were able to deploy that. We're working to deploy that on a web app, so then it can be a little bit more interactive. So let's jump into that. So the data set that was used for this whole project was the Free Music Archive data set. In the field of music information retrieval, this is a very popular data set. I used their smallest subset. So this is comprised of 8,000 songs. Each of them is trimmed to a 30-second clip, and all 8,000 songs are balanced across 8 genres. So meaning there's 1,000 songs per genre listed here. Also not listed, but there is metadata associated with those 8,000 songs, namely things like the genre, which we need to do our classification, the date that the song was created, the artist who wrote the song, the composer, etc. And that data turned out to be very sparse. So in the next slide here, one of the biggest insights that I was able to gain from EDA, exploratory data analysis, was looking at the tracks per year per genre. So this graph is a little bit busy, but what I want you to take out of it is that you can see that over this roughly 10-year span from 2008 to 2016, we see that most of the genres are fairly balanced, staying at the same number of frequency, like number of tracks per year, barring this outlier where instrumental seemed to draw a lot of its 1,000 songs from the year 2015. Now, why is this important? So what this means for us is that our data is a little bit more robust. It comes from a wide distribution being across a 10-year span, and it's fairly evenly balanced. And so we hope that if we can train our models using this data, that our models will be more robust in case there were, annual, monthly trends in the music. If a genre had any changes over time, it will be able to handle those better and still detect the same genre, no less. Coming right into the model architecture, for the sake of brevity for this presentation, I'm only showing the final model. It is a CNN LSTM hybrid configuration. So the first 3 core layers or cells here are comprised of convolutional one-dimensional layers, and they're part of this feature extraction section. So the idea is that you're taking raw input, being the audio preprocessed to an image, to one-dimensional data, and you are feeding it into these convolutional layers, which are hopefully extracting minute features about the music. So namely like a drum beat or a guitar strum or incremental pieces of audio, and building up to larger and larger pieces until finally you feed it into this LSTM layer, which can then take that process data and identify longer term temporal trends in the audio. So namely, now that we have all of these little strums, beats, what have you, we can determine the rhythm, the cadence of the song, which would help identify, hopefully inform the model to help identify the genre of that song. So coming to the performance, again, covering the final model that I employed, going off of a baseline, the baseline model yielded roughly 12.5% accuracy. This makes sense considering we have 8 genres. So roughly a 1 in 8 chance choosing at random, it would give you a 12.5% accuracy to pick the appropriate genre. Coming to our model, the CNN LSTM hybrid, we were able to improve from that 12.5% all the way up to 49.3%. This was at 40 epochs, if you know what that means when training my model. And so roughly a 37% increase in performance. Worth noting, I chose to use accuracy as my main metric for measuring performance for these models because we're not particularly interested in one genre over another. We want to see that this model can reasonably predict all genres equally well. There is no reward or penalty associated with any one genre. So I deemed that accuracy would be the best metric to reflect that performance. And finally, now that we have our finished model, or at least an MVP, we can take it, and I'm working to deploy a web app, which will be a little bit more interactive, and you could take any audio, your own audio, upload it on there, and pass it through that model to generate this radar chart. And so again, given the eight genres that I listed earlier, my model will predict whatever audio you fed into it, which genre it thinks that falls into. And so in this example case, we can see that it's highly likely, or the model believes very strongly, that the song that was passed into it was a folk song with maybe some elements of rock present in there as well. And I think that is all from me. If there's any questions, I'd like to open it to the floor.
Thanks so much, Ken. Can you talk a little bit more about your model architecture?
Sure. So there's a lot going on, but I didn't mention it in the actual presentation, but each layer, the convolutional one-dimensional layers, the LSTM layer, they all have batch normalization, pooling, and dropout present in them. So in short, the pooling and the dropout are there to mitigate overfitting. And so for whatever reason, my model was extremely prone to overfitting on the training data, meaning that it wouldn't perform as well when predicting on data that it hadn't seen prior. And so I applied pretty heavy pooling and dropout across all the different layers to try and mitigate that, as well as batch normalization along every layer to accelerate the training of the model, especially since we're working with a smaller data set, and that seemed to yield performance improvements. So.
Thanks, appreciate it.
Sure thing.
Any other questions for Ken? If not, we're coming up to our second last speaker. Oh, sorry to jump the gun. Tiffany Garcia says, hi, Ken, great presentation. Thank you for sharing. If your model included more genres than 8, do you think it would perform better or worse?
Okay, perfect. Yeah, thanks, Tiffany. Also, hi. She's a friend of mine. But great question. So in this instance, I only used 8 genres because that was the data set that I was able to find that was workable for the sake of my project in a week's span. That being said, I think you could totally expand this project. And in fact, again, that Free Music Archive where I got the data from, they have larger data sets that are comprised of 16 different genres. And it's not limited to that. You could scale it to whatever you like. Granted, the performance might be a little bit worse out the gate because inherently you're choosing between more genres, but you can definitely take this model in its current state and apply it to more genres, less genres, whatever you like.
On that note, it strikes me like a song could fall into multiple genres at the same time. Could you expand or change this model to predict many genres instead of just one?
Absolutely. So without going under the hood too much, this problem can get a lot more complicated if you want it to. And so inherently, right, as a music listener, you know that songs are not discrete. They're not exclusively rock. They're not exclusively pop. There's pop rock songs and like every other, combination of genres. So it's actually in a naive way, it's kind of asking a lot of a model to be able to discern songs into a singular genre when that's not exactly the case, right? And so this model can definitely be expanded upon to also do multi-class prediction. So meaning that in the output, when it gives a result, it will be predicting for multiple genres or a single one if it deems that it's only this genre. And funny enough, I think that once the model's been pre-trained and set up, it might actually yield better performance if you allow it to pick multiple genres, because the model may know that like, this isn't this or that, it's kind of both. But because we forced it to choose only one genre, it's restricted to giving just that. And so if you could get data with labels, meaning like the correct answer, suggesting that it could be multiple genres, I think that this model has a lot more room for growth, in fact.
That's really interesting. Thank you so much, Ken.
Thank you.
Great presentation. And then, as promised, we're moving on to Laura Nguyen. Laura has experience as a machine learning dataset analyst at Amazon and search engine analyst at Yahoo. And tonight, we'll be speaking about how to prevent sex trafficking by identifying hotel chains using machine learning. Laura, you've got the floor.
Thank you, Michelle. I guess I'll close us all out. Hi, my name is Laura Nguyen, and I am presenting on how we can use hotel room images to identify hotel chains and prevent sex trafficking. Sex trafficking in the United States is a hidden problem that people know exists, but little is being done to prevent it. It's estimated that roughly 400,000 people are victims of sex trafficking each year in the United States. Before I talk about my dataset, I want to point out that in 2019, 12 major hotels were sued for their reckless inaction and role in the sex slave trade of women and children, according to Reuters. Hotels are inadvertently profiting off of these crimes. Many victims' images are shared in these hotel spaces. So what if we use hotel room images to train a model to predict what hotel chain the room belongs to? So a little bit about the data. I have 1 million hotel room images from Cornell, which was gathered from travel websites and the app Traffic Cam. And our goal is to predict hotel chains, specifically 6 hotel chains. As you can see on the graph on the right, each of these 6 hotel chains has a listed number of images. And that would total 14K training images and 3,500 testing images. Here we have a sample of images per chain. You can observe that there aren't many obvious patterns or differences that make a hotel room unique. Some locations have pools, spas, and other amenities that would distinguish them, however. So, how well can a machine perform at hotel chain prediction? My base model received an accuracy score of 24% at predicting the most frequent hotel chain, the Hilton. My first model received a test accuracy score of 62%, which is great. However, the test accuracy score is 22%, which indicates that there's overfitting. In order to make convolutional neural network models better, we must adjust the structure of the model. And to prevent overfitting specifically, I increased the dropout rate and decreased the learning rate. I also increased epoch size and batch size. And these may seem like easy tasks, but it's worth noting that the higher the epoch size is, the more iterations there will be. The lower the learning rate means that the model will take much longer to learn, which is a good thing, but it takes a vast amount of time. And Model 3 has a fairly low accuracy score of predicting hotel chains, but it beats the base model and has potential to improve with more epochs and hyperparameter tuning. So although the model isn't quite where I want it to be yet, it's still pretty amazing that a machine can correctly predict 25% of the time of the hotel rooms. Or hotel chains, excuse me. And as I mentioned, I'm looking forward to adjusting the structure of my model by increasing epoch size and reducing the layer sizes. And additionally, I think more organized data is helpful. And I'm also interested in introducing transfer learning in future iterations of this project. Thank you. I made it. I will take questions if there are any.
Laura, you mentioned transfer learning at the end. How do you think a transfer learning model would do on this data set?
I think if I can find the right data set to apply, use for this to apply transfer learning, it might improve how well the model predicts or detects labels or chains.
Yeah, I'm also hoping that if you have the power of a model that's pre-trained on a lot of images, specifically rooms, that that will help with the smaller data set to be able to distinguish these fairly fine-tuned features that your model will have to look for in identifying these different hotel rooms. And that you could also then scale it up to a bigger data set.
Yeah, the 1 million images.
I also have a question, Laura. I hope
Sure.
this isn't too left of center, but it's actually curious. Like when you were starting the project, like when you were in ideation trying to think about what to do, like we're trying to get to the bottom of sex trafficking, right? So was there any particular reason that you started with the hotel angle as opposed to like maybe building like a machine learning model for like, I don't know, finding specific like culprits or perpetrators or things like that? How did you come to this data?
I just found it and it really interested me. So part of my background at Amazon, I had to help detect furniture for the apps. And so I was looking at a bunch of items that were related to my past. And this was similar. It's rooms. It dealt with rooms. It dealt with not necessarily furniture, but, you know, bedding and whatnot.
That's awesome. Thank you.
Of course.
Laura, so obviously this is a very difficult problem. What was the most challenging part of this for you with the project?
So much, so much. I mentioned this in prior sessions, but I looked at this and I was thinking, wow, this is such an amazing project. I would love to like contribute somehow. When I got the data, the images were, you know, they were all there, but accessing it was difficult. I faced so many roadblocks. Then I had to work with AWS and that was a pain. And I mentioned prior as well that I ended up working locally rather than using a cloud storage system. I'm sure most of you have dealt with issues as well, similar issues.
What was the most fun part about this project for you?
I think the fun part was finally being able to model, finally being able to use the images I had and feed it into the model and get a result. The result wasn't as great as I expected, but you know, detecting rooms can be very challenging.
All right, then seeing that we're at about 7:30 already, we've got one last speaker for the evening, and that is Nathan Berkeley. Nathan will be speaking about identifying astroturfed reviews, fake reviews, and Yelp data. Nathan, you're up.
Hi, everybody. My name is Nathan Berkeley, and this is Identifying AstroTurf Reviews. The problem: fake or AstroTurf reviews have become more common as shopping continues to move online. AstroTurfing is the practice of writing a fake review to inflate scores of a product or service which compromises data integrity. The data set: 700,000 total restaurant reviews from Yelp. 56% of them were real, 44% were fake or AstroTurfed. 12% of the reviewers were a one fake review entry only. The biggest spammer was 1,700 fake reviews. 65% of their total reviews were fake. And the most AstroTurf restaurant had about 99% of their reviews being fake, which is insane. My first round of modeling in EDA was essentially NLP focused only. As it turns out, the models don't actually perform that well with NLP features only. Typically, when you have an NLP problem, one of the first things you test is you build a dictionary of unigrams, bigrams, and trigrams. Not only is that not very effective by itself on this data set, but trigrams actually significantly reduces the model's effectiveness. So following the CRISP-DM process, I did a second round of EDA. I engineered some different features related to punctuation, I also investigated if there was emojis, that there were not. As it turned out, unfortunately, none of the punctuation, word count, sentence count ended up being very useful to the model, but funny count, cool count, useful count, and rating were all potential candidates that were identified by this. I ended up figuring out that of those, useful count and rating actually did improve my models. In terms of model performance and metrics, I chose precision to be my metric because even though in a typical fraud case, you're probably more concerned about recall, because when you let a fraudulent event through, you're talking about some monetary loss, or you're talking about a security breach. In this case, most of the time, a product or service is not going to be more fake reviews than real reviews. So we want to make sure that we're not discarding more real reviews than we are the bad reviews. That would just further dilute our data. So the baseline is just a 50% guess. And from there, I tried, 3 of the supervised models with naive Bayes, random forest, logistic regression with NLP features only, as I discussed earlier. They were all around 60%. From there, I pivoted to RNN, recurring neural networks, GRU and LSTM. GRU clocked in at about 66%, LSTM about 67%. I spent the bulk of my time trying to tune the hyperparameters for the LSTM. Long term, I think that LSTM is the most promising model, but for now, due to time constraints, I had to put it down, and I basically went back to logistic regression with the 2 new features, and that's now my best performing model at just under 70%. I also wanted to benchmark my model's performance versus other groups. The OT group used to have the best technology on the market for this, using an SVM model. My logistic regression model outperformed them by 2%. And then the Bing Liu team, who I got my data from, they have the best performing model currently at 86%. I wanted to show an example of a fake review that was written very well to kind of show what I'm trying to work towards being able to detect. Currently, my model would struggle with this because, as I mentioned earlier, unigrams and bigrams by themselves are not very useful, and none of the words on this list are going to be highly correlated with being a fake review. And then furthermore, if you look here, the useful count is very high. So this is actually a very well-written fake review. It looks like they were able to trick a lot of people. In conclusion, it is difficult to identify the AstroTurf reviews with high precision using conventional modeling. Adding non-NLP based features such as rating and useful count improve logistic regression. However, in order to deploy the model, it needs to be more precise. That way I'm not discarding more good reviews than fake reviews that are being filtered out, because that would just further dilute the data. As I mentioned earlier, the next steps, I need to investigate the structures of the reviews that avoid detection to improve my domain knowledge. The Bing Liu group has spent over 10 years researching this, so I'm pretty sure that's a big part of why their models are effective, is they're really experts on this topic. And with better domain knowledge, I need to engineer more impactful features. Here are my sources. I got the data set from Bing Liu and the rest of their science team. At this time, I'm going to open it up for questions, and if there's no questions, there's a few quick topics I'd like to talk about that I found interesting.
Hi, Nathan. My name's Chris. I'm a prospective student at Galvanize. So I found your presentation really interesting, and I think that processing text and trying to find things like tone and it's a very challenging problem. And to me, it seems like improving the features, like feature engineering, could improve it a lot, because you showed that the Pearson correlation coefficients were kind of small. So do you have any other ideas, like potentially in the future, of how to define the features and add new features?
Yeah, thanks for the question, Chris. I'm actually really glad you asked that, because that was going to be some of the things I was going to talk about. So one of the other things I thought about exploring was this AstroTurf restaurant that has almost 99% fake reviews. What I noticed is that almost all of them have a high amount of profanity. So I thought to myself, okay, well, what if some of the more poorly written fake reviews have, a higher count of profanity? And then when I was kind of snooping around, I noticed that wasn't really the case. And I took a closer look at it. This restaurant is a heavy metal themed restaurant, so maybe that was contributing towards why that was skewed. So that was one of the things I thought about looking into. As I mentioned earlier, emojis would have been something to look into, but they weren't in this data set. One of the other things I looked into was, to clarify, one of the things I didn't want to use though is I didn't want to use reviewer ID information. And the reason why is because when you use reviewer ID information as part of your features, that's helpful for, finding, repeat offenders, but it makes it harder for your model to predict a one-off offender, like just a burner account, a bot, or just, someone who writes, one review and then they get caught. Because it's possible that Yelp has developed technology good enough to do it. I think that's why there is such a high percentage of the population being, one-off reviews and then they're caught. The problem with all three of these models right here between all the groups is that they actually all struggle with one review. In my case, it's just because I need to make my model better. Even with the best technology, basically how they do it, Chris, is they look at someone who has, say, maybe 10 reviews, right? And, if say on the 11th review, their personal voice, the style of their writing is just very different, they'll mark it for review. And I think that's part of Yelp's algorithm, but that's how this other group was able to, be very successful. Is they basically only looked at people who had multiple reviews, and they were able to find out, hey, this is very weird that they would write, their sentences this way. Their paragraph structure is a little weird here, and they were able to kind of figure that out. But like I said, the problem is that what happens if your population is only one-off reviews? Your model's not going to perform very well on that. Outside of that, I honestly just need to do more research. If you're interested, I can link you all of their research, and I can talk to you about it more later. But there's just certain patterns that develop over time, and I was kind of hoping that the LSTM would do that for me, but I didn't have enough time to work with it. Because with the LSTM models, you're inputting sequences of data rather than, a unigram or bigram, so it's a little more complex data. So sometimes, with these neural nets, it can kind of do the heavy lifting for you and figure it out on its own, and that's what I was hoping for.
Thank you.
Thank you. Any other questions?
Are there any other promising features that you'd like to look into, Nate?
Okay, so off the top of my head, no. What honestly surprised me more than anything was, and this is also to further answer Chris's question, when you work with an NLP data set, oftentimes the feature weights that you pull out, because you can use code after you've run your fitted model to figure out what's important. If you need a vocabulary of 50,000 words to be, to be even somewhat functional, like at the point I'm at, the weights are going to be very, very low. So I know you mentioned, Chris, that, these, as you said, these are obviously very small correlations. Comparatively speaking, they're huge, though. That's why, even adding something that's, negative 11 and 3, that made a huge difference, just because comparatively speaking, that was pretty powerful. But yeah, what I was honestly hoping for, I know it's going to sound dumb, but I was hoping that maybe with the fake reviews, they might be more lengthy or, less verbose because they're trying not to be suspicious. But no, I think it was only like a difference of 7 words per review, which might sound like a lot, but it's really not when you're comparing, 160 to 153. The sentence count was almost exactly the same, and the punctuation count was almost exactly the same. Another thing I thought about doing too, if I have more time, it would be interesting to see if maybe some of the more poorly written reviews had weird punctuation patterns, because for most of my models, I would standardize it by lowercasing the data first, so I didn't investigate that. But, that could be something to look into. It's just that the problem, I think, with that particular approach is like, this is a raw review. This wasn't any modification. So, most of the reviews that I'm going to have trouble detecting are looking like this. What I'm going to assume happened when the two groups figured out this was a fake review was they probably looked at this, like I said, and figured out there's a stylistic difference. Another thing that's worth noting too is they said they visit regularly for Michigan. If you have the person's IP and it's not a Michigan IP, or if like, you know, their account listing is in, you know, say Arkansas or something, I don't have that information, but if you have that, you know, that's certainly something that can be linked to it.
Thank you so much, Nate. And then, unless there are any other burning questions, I'm sure you folks would all like to go grab some dinner, and our speakers tonight would like a rest. So thank you everyone for attending. Thank you to all of our presenters for all of the work that you've put into this, not just today, this week, but also over the last 3 months. We appreciate it. So with that, I think all the galvanizers can meet back in the main room. And thank you everybody for coming.